Good afternoon. This is CIVE 638, Sedimentation Engineering. I'm Professor Victor Ponce from San Diego State University, and today is Tuesday, August 30th, and this is the first class of the second week. I'm going to open up the material at this point. Bear with me a little bit. So let's go then to the syllabus. And we are currently looking at sediment transport, initiation of motion. Can you see the graph where we ended last week? So this is such an important graph that I am going to stress on it today, making sure that you all understand and memorize the concepts that are contained in this figure. We have total sediment load, and there's two ways to classify them, and they are a bit confusing because they have a tendency to use the same name. So based on the predominant mode of transport, the total sediment load is classified into suspended load and bed load. And why a difference? Why not one? Because the bed load has a different mechanism. It travels by jumping, sliding, and touching the bottom, while the suspended load, by its own name, it's suspended. It's not touching the bottom. There are formulas for the calculation of suspended load only, or formulas for the calculation of the total sediment load, meaning suspended load and bed load. There are that I know of, about 50 formulas for sediment transport that have been put together over the years. One of the earliest formulas, I believe, was the Shockley's formula, which it's dated around the turn of last century. So it's about 100 to 120 years. But since we've had many formulas by proper name, the most common or the most popular, not necessarily popular, but well recognized, are the Einstein formula, the modified Einstein formula, and the Kolbe formula. Those are the three major ones, but I can tell you there's 50 of them. And I'll endeavor to show you graphs where many of these sediment transport formulas are plotted in only one sheet of paper. Okay, the second classification is based on whether the particle sizes are represented in the channel bed. And that includes wash load and bed material load. Wash load is not supposed to be calculated because it washes through the system. It's typically the fine material. In a sand bed channel, the wash load will be silt and clay. And when I say sand bed channel, I stress that because the sand bed channels are the ones that we engineers typically are looking into and calculating them because it's required. Many of the rivers that we study are in the valleys, and in the valleys, the bed is composed of sand. If we move upstream, the bed may have some gravel. As a matter of fact, there are upstream in the mountains, there are some gravel beds that are not necessarily, they don't have any sand for that matter. And if you go further down to the estuary, where the velocity of the flow starts decreasing because of the proximity with the ocean, then we can have some silty beds, or beds that have some silt in it. But it's not typical. Most of the work that has been done in sediment transport by engineers, by hydraulic engineers, is in the sand bed channels, in the middle, in the valleys. Okay, so also let me say at this point that no formula computes wash load. There's only one exception. The only formula that computes wash load is the modified Einstein formula. It's supposed to be the most complete, the most theoretically appealing formula, and that's what we use when we want to get at a complete answer. We try to use the modified Einstein, and the reason why I say try to use the modified Einstein is because it has a drawback, a slight drawback. It requires data. And sediment data is extremely difficult and expensive to get. So if you don't have any data, you can't use the modified Einstein. But you could use the Kolbe or any other methods that are out there. And the usage of this or that method is a particular choice. So let me keep going on here. And now we're going to go to the subject of initiation of motion. Right there. By the way, this paper or what you're seeing on the screen in there is part of my hydrology book. Hydrology book? What does sedimentation have to do with hydrology? And the answer is in 1989, when I figured out that I had to write a book in hydrology because I was teaching hydrology in and out. Uh, but I decided to add, I had figured out that I would do 10 chapters to cover 10 subjects in hydrology from the beginning to more or less the end of hydrology, which is the modeling of the catchments. Um, but then I decided at that time that the book was going to be incomplete if I didn't add a few other chapters, which were not necessarily dealing directly with hydrology, but they could be considered part of hydrology. And one of them was groundwater. So I added groundwater. I also added snow. Then I added also modeling because that was important and it's still important. And at the end, I decided to add a chapter on sediment transport. And so I did. Typically, a hydrology book does not have any sediment transport. If you want sediment transport, you got to go find a book on sediment transport. And there are a few. I think my professor, Daryl Simons, has a book that he authored on sediment transport. And many other people have written books on sediment transport, not just in the US, all over the world. Okay, but this is then an exception. An exception meaning that this is a hydrology book, but yet we are talking sediment transport. And the reason why I did that was because I felt that I was knowledgeable and I felt that I was not going to have a chance to talk about sediment or write a book on sediment because I wasn't teaching undergrad. Sediment is not usually taught at undergrad. So therefore I did this. So that's why you're reading, you're benefiting from the circumstance that I had to add a chapter on sediment transport in my hydrology book. So initiation of motion, what is that? Channels, open channel flow carry sediment, particularly if you have a natural condition, a river. A river is always carrying sediment. Why? Because it is always entraining the sediment from the bottom. As a matter of fact, it's been said that the rivers are authors of their own geometry. That's exactly what they do. There's an interaction in there between the geometry, the hydraulics, the sediment, and so forth. So rivers are creators of their own geometry. So they move the bottom. The bottom of the river is moved, and there is a constancy of or a balance of the sediment coming in and the sediment going out in a controlled volume. If there is no balance, for instance, if there's more flow, more sediment going out that is coming in, then you'll have erosion. You'll have what is called degradation. Otherwise, if you have more sediment coming in than going out, you'll have aggradation. These are typically they are called non-uniform situations. And they are difficult to control or to calculate. So the best, easier calculation of sediment would be when it is under steady conditions, meaning the sediment going into the control volume, the amount of sediment going into the control volume is the same as the amount going out. Questions? Okay. Okay, so then we have in here, water flowing a stream bed has a marked velocity gradient. This velocity gradient exerts a shear stress on the particles lying on the stream bed, and therefore the shear can be approximated by the following formula. Tau equal gamma ds. Now, I present to you this formula at this point because I believe that you should already know about it. But the fact of the matter is, many of you may not know about this, may not have heard. You would hear about this formula had you taken open channels, 530. But I know positively some of you didn't. So what I am going to do in here is I'm going to lead you to the place where this stuff is being discussed in some of the material that I've already shown that I have put in there. So what I did this morning, I did this. Right after here, I have an item that says tractive force, section 6.3 in fundamentals of open channel hydraulics, tractive force, right there, tractive force. So in this section, I derive that formula that I already shown you. And in here, you can see the control volume and the hydraulics that is necessary to get to the formula. And that is given by a balance between the acting gravitational force, which is equation 13, and the resisting frictional force, which gives us, by equating these two equations and doing the corresponding hydraulics in the geometry, we get to this formula 615, which says tau is equal to gamma RS. It's quite the same as what we had discussed. Remember, gamma RS, where gamma is the pressure. Excuse me, can you silent your video, please? Gamma RS. Now, if we go back in here, you will see gamma DS. So what's the difference? YR and YS? Well, R is the real value, but oftentimes, since we're talking about hydraulically wide channel, we can replace the R for the D, which is the depth, the flow depth in a channel. Okay, so that's a formula, and I already told you how we derived it. And that's exactly what I'm going to do in the future. I'm going to refer, if there's something I consider that is new material for many of you, I will refer you to the location so that you can go back and study it on your own. Again, why initiation of motion? Because you do not want to design a channel, particularly, let's say you're designing a channel, and you got to consider that at the entrance, there may be some sediment coming in, right? You can't control it. There's always a possibility that sediment may get in because the water, the flow comes from nature, and nature is picking up the sediment. So once you get in, this is what's going to happen. If the channel, the slope of the channel is too small, the sand will settle in the bottom. In unusual situations, that sand will clog the bottom. It would just, the channel would become inoperable. And this has happened in many places. So we need to know the concept of initiation of motion so we are able to place the channel or design the channel in such a way that the sand at the bottom is always in movement and is never stopped or cannot stop and settle. Because if it starts settling, then more particles will come in and settle, and eventually the channel will be clogged, and we would lose the function of the channel. So initiation of motion then becomes a very important subject in our field. Fortunately, we have the Shields diagram for initiation of motion. Who is Shields? Shields was an American gentleman that went in the mid-30s to Europe, specifically to the Swiss Polytechnic. I think it is a good school, Swiss Polytechnic, somewhere out there in Switzerland. And he wrote a doctoral thesis and developed this curve that became the curve to use. 1936, and today is 2022. So this chart is exactly 86 years old, and it has not been superseded. Isn't that amazing? What did he do? Well, he was in the laboratory. His advisor probably told him, we're going to be looking at initiation of motion. If you can develop something that is a contribution in that field, then you will get a doctorate degree. And that's exactly what he did. He identified the X and the Y in this graph. And that's not easy, by the way. I've done this sort of thing in the past, not with initiation of motion, but I've done it with many other problems, trying to figure out, what are you going to plot? What can you plot in order to get an answer that you want to? Let me sidetrack in here. I have a creation of mine dated 1976, 77, that I call the S-curve, but it is a plot of wave propagation, but it is dimensionless plot, just like the Shields curve. And therefore, I had to figure out what to plot in the abscissa and what to plot in the ordinates. And since nobody had ever done that, solved that problem prior to my getting into it in 1976, it was a difficult thing. It was a trial and error. We had to have a hunch, and the knowledge, of course. And finally, we had to have the luck. Luck has to be always with you if you're going to accomplish important things. Okay, so let's go back to Shields now. Shields identified the abscissa of his curve, and he called it the boundary Reynolds number. It's a Reynolds number. You know the Reynolds number is a ratio of two viscosities. The viscosity in the numerator is like a macro viscosity, but it's a special type of macro viscosity. It's the U star times the ds. In the denominator is the micro viscosity. That's the viscosity of the flow itself, or the water itself, represented by nu. This is the kinematic viscosity as opposed to the dynamic viscosity. And you know, there's a relationship between the two. If you can't remember this, go back to your studies of fluid mechanics. But we're using here the nu, which is represents the kinematic viscosity. In the numerator, we have U star times ds. U star is what Shields call the shear velocity, and ds is the diameter of the particles, the diameter of the particle. So he introduced the diameter of the particle, right? ds is the mean particle diameter, and U star is the shear velocity. When I looked at this for the first time back in the early 70s, when I was going to school at Colorado State University, I got confused about the shear velocity and didn't know why he had done that. He had done it for some reason. The reason was that if you put into the shear velocity, the whole thing was going to plot nicely. Note that it plots nicely, but it's not 100% correct. But he did what he had to do at the time. He was the first person that was able to do this, meaning develop a dimensionless plot that will separate motion over here from no motion at the bottom. In the ordinates, he figured out that he could do this best using the definition of the dimension of shear stress. And we already know what shear stress is. I already told you what shear stress is. It's gamma RS. It's not here. It's in that other page. Gamma ds over here. That's the shear stress. So he had to dimensionalize the shear stress, or make it dimensionless, by dividing by some kind of stress. And the stress that he chose was gamma sub s minus gamma times the ds. So the particle size, as you can see, enters in both the abscissa over here and the ordinate in order to make both abscissa and ordinate of the Shields graph dimensionless. Great creation. The shear velocity is defined as follows. And at the time, I remember this. I was looking at this yesterday, today. I remember this. I said, what the heck is this? Never heard of the shear velocity at the time, back in the middle 70s. But later, I have done a lot of work in this area. I spent almost 50 years working with these equations, early at the beginning. And I realized that the shear velocity is a way of expressing the velocity, only that affected by a frictional constant or a frictional factor. And the frictional factor turns out to be a readily identified frictional factor, which is it's exactly 1/8 of the Darcy-Weisbach. So why Darcy-Weisbach over here? Aren't we used to Manning? And the answer is no. There's actually 5 ways to express friction in open channels. And I'll endeavor to get back to that later on. But at this point, what we need to realize is that if you look at this equation and you square it, on the left, you're going to say U star square, which is the square of the shear velocity. And on the right, you're going to have tau over rho. And rho is the mass density. And if you get the mass density to the left, then you're going to have U star rho equal tau square, tau equal tau. And U star rho equal tau is gonna tell you that this is basically related to the quadratic formula for friction, the frictional quadratic formula, which I briefly talked about the other day. You can review back what we had done. I do believe that quadratic formula that I'm talking about here right now will be used by you in one of your homeworks. I believe it's this homework, the homework that is due next week. I think I'm quite sure on that. So the quadratic formula will come back and we'll have to use it. So this is basically a reflection, a nice way of putting the quadratic formula together. Okay, so that is then the definition by Shields. The Shields diagram indicates that within a mid-range of boundary Reynolds number, approximately from 2 to 200, let's take a look in here, from 2 to 200, that this thing in here is going to be almost a constant, and the value is going to be 0.04, roughly, so roughly 0.04. So a lot of people that want to use the Shields graph, we would take the critical tractive stress is equal to 0.04. And when that's the case, then we get this, the critical stress is equal to 0.04 times the diameter. Now for quartz particles, that reduces to 0.34 times the diameter in the proper units, of course, in American, or rather US customary units. Critical tractive stress given in pounds per square foot and particle diameter in inches. It's interesting in here that we should realize that units play a very big role in sedimentation and sedimentation engineering. And oftentimes we find ourselves working with the US customary system, but yet the diameter of the grain is given in millimeters. You wonder how that happened. As a matter of fact, many methods, I can tell you, I know for a fact, many of the methods use always the diameter in millimeters because most people are used to diameter in millimeters. That's all I can say. And you know, millimeters is not part of the US customary system. The appropriate unit would be inches, as is shown in here. We also mentioned Mr. Lane. Lane is my academic grandfather. I already told you that. He was a professor of Daryl Simons. So he turns out to be your academic great-grandfather. Lane has shown that the coefficient is around 0.5. Lane did extensive work in the 50s, 40s and 50s. So a little bit, a couple, maybe 10, 15 years later than Shields. And Lane's value is 0.5. So there's some consistency in here, 0.34 and 0.5. And the discrepancy is more understandable when we realize that Lane was using D75 particle size instead, or as opposed to the D50 used by Shields. Shields was using the mean particle diameter. And Lane, for whatever reason, I'm not privy to why he did this, but he was using the D75. Now, all of you have taken soil mechanics as part of your civil engineering studies. So you must be familiar with the grain size analysis and the grain size distribution. So this is all there is. It refers to the diameters and the grain size distribution. Okay, so now let's move on in here, and we're going to show an example of this calculation. Example 13.6. Based on the Shield criterion for initiation of motion, determine whether a 3 millimeter diameter quartz particle is at rest or moving under the action of a 7-foot flow depth with channel slope 0.0001. Assume water temperature 70 degrees Fahrenheit. So we're going to be doing this again. We're going to be doing this in US customary units, and yet we're talking about a 3 millimeter diameter. I told you there's confusion, but all I'm doing is reflecting or practicing what is practiced in the field. So from here we go on, and I'm going to go over in detail because it's necessary at this point since you're beginning this study. From equation 13.4, the bottom shear stress is tau equal. So 13.4 is this one. 13.4 is over here. Right, there it is. There's equation 13.4. We already covered this. As a matter of fact, I believe I asked you to calculate that equation in the homework. So from equation 13.4, I'm not going to go back in here because I'll get lost. Okay, here we go. From equation 13.4, we get this equation. From equation 13.17, which is right over here, I'll do that. From 17, that's 17 over there, we get the dimensionless tractive stress. Then from 316, we get the shear velocity. 316 is this one over here. Can you see 316? Yeah, that's the shear velocity. The shear velocity. From table A2, the kinematic viscosity is, what is this now? We need the kinematic viscosity because we have a water temperature 70 degrees and we're going to be using the kinematic viscosity in the calculation. So we need to go to table A2, and I have not made the table clickable in here, but table A2 refers to the appendix of this book. So it's in my hydrology book appendix. Where are you going to find that if you want to verify that the kinematic viscosity is indeed 1.058? You go to the appendix of the book, which is at the beginning, right over here. Here. Engineering hydrology, appendix, right there. Can you see that? That's easy. That's easy enough. Where am I? Okay. No, that's not it. All right. There we go. Okay, I'm getting confused in here. Okay. The kinematic viscosity, we already know where it comes from. The boundary Reynolds number, by definition, from equation 315. 315, right there. Boundary Reynolds number, by definition. For boundary Reynolds number equal to 140, the dimensionless critical tractive stress from the Shields curve is 0.048. And since tau star is 0.0431, which is from over here, is less, then it is concluded that the particle is at rest. That would be the end of this calculation. If we use online shields, let me see if I can get this thing right. US customary particle diameter 3 flow depth, channel bottom 0.001. I'm hoping that I am remembering all this data correctly. We'll see. That's right. That's right. Dimensionless tractive stress tau star 0.0431. Dimensionless critical tractive stress tau star C for critical 0.048. So 48 is moving, 43 is actual, so there's no movement. The particle is at rest. So that's the end of this calculation. Note that I have given you quite a few of these calculators, oh, maybe 4 or 5 of them. So you will simplify your work, and I have featured these calculators in the homework. So you could do 2 things. You could do this calculation the way I've done it here, manually, so that you can learn where it comes from. And you can use the calculator and get the answer. Or you can forget about the manual calculation because this thing looks straightforward and you can just go to the straight calculator. So I'm not going to, when I present a calculator, I am not going to require that you do it by hand because I trust my calculators and I hope you will trust them too. So again, the fact that the calculators are there is only for the purpose of simplifying your time involved in the learning. But if you want to do it hand in hand, or rather by hand, you can do it. It's all in there. It will take you a few more minutes. Also, you can verify that in fact the calculator is correct, as we have done in here. Every once in a while, I got more than 300 calculators in all sorts of topics. Every once in a while, like once every 10 years, I get somebody that says that I made a mistake, by the way. As a matter of fact, in my entire career doing these calculators, which go back to the year 2004, that's 18 years, I've only had 2 people correct me, and they were correct, by the way. That means nobody's perfect. I can make mistakes too. Okay, so for that, then we are going to finish over there. I finish over here too, and I'm going to go back now to the issue of the same question. This is a fascinating issue here, which continues the work that we're doing, that we have done in sedimentation. The first thing I'm going to do is show the video. Let me say that in the past, I used to pose this problem as homework. But then it became apparent that it was a difficult problem, and only half of the students were able to come up with the answer. So I decided to go ahead and open up the solution. And furthermore, I had a student of mine, a very smart gentleman, very mathematically oriented. I realized that. So I tasked him with actually solving the problem, the complete problem. And that's what I'm going to show you tonight. the solution of the complete problem, not just posing of the problem and asking what would be the shape of the profile, as was the original intent of the story. Let's take a look. Do you see the video? Margot?
Yeah, we do.
Okay.
During my college days at Colorado State University in the mid-70s, the hydraulics graduate students at the Engineering Research Center were well aware of what it took to conquer the hurdles. Professor Darrell Simons had a reputation for toughness. However, he always asked the same question on the preliminary exam. If you drop a spherical particle in a flask full of water, what is the shape of the velocity profile in the space between the particle and the inner wall of the flask? Everybody knew the answer. However, Professor Simons invariably started every prelim exam with the famous question. One day, a student worked up some courage and asked,
Let me interrupt this because at this point I'm showing something very important. This is a fused spillway in the La Leche River in Lambayeque, Peru. I had a project back in the year 2007, 2008, no, 2008, 2009. I was going to a project in northern Peru for 2 years. I would go there like every 3 months. And I ran into this project, which I thought was really fascinating. I had heard about these, but I've never seen one. So when I was there, I promptly took a picture of it. What is this? This is a fused spillway. My understanding is there are not that many around the world. I've seen pictures of 3 or 4 fused spillways, but not more. I know the Bureau of Reclamation built one, I believe it was in New Mexico, a famous fused spillway. Now this is not a famous fused spillway, but it's certainly one that is still up and standing. The fused spillway is designed to fail. That's why it's called a fuse. You know, a fuse is the first thing that fails in a system, right? Like an electric fuse. How does this thing work? Okay. This La Leche River is known for having unusual floods. And the reason for that is because half of its watershed is dry and the other half is wet, which is kind of an in-between, no man's land. If it were wet, it would have consistent and voluminous floods, regular floods, right? But if it's dry, the floods don't come. But when they come, they have a tendency to be extremely high. Extremes of floods happen typically in arid areas. That's just the way Mother Nature put it together. So this is a spillway. But how is it designed to work? Well, here, this, by the way, is an intake. So they have to have a dam in here. This is the dam over here. I'm pointing at it. And that's the spillway. That's the overflow, spillway, and the dam. So this is an intake. There's a channel over here. This over here is the entrance to the channel. And this is an irrigation channel. Intake to an irrigation channel. So what's this thing doing over here? This is what the fused spillway is. It so happens that since this watershed is not well behaved in terms of flood predictability, the designers in this place, what they have done is they have put a fused spillway in here. In other words, the flood would go right behind the trees over here, but if the level of the flood gets above this stage, it'll go over the spillway and it will breach, it will break within an hour. I expect this to breach, to be gone, totally gone within an hour. Notice that over here, this is not going to go because this is concrete. But over here, this is going to go because this is sand. It's actually put together to fail. It's a fused spillway, okay? So over here, if and when it has not happened yet, and I believe this is still there as far as I know, but when it happens, when the water flows over this level, it'll destroy the spillway and it will open up the spillway 2 to 3 times its capacity. In other words, the flow would now would be free to flow in here, which was not possible for it to flow while the spillway was there. This is typically a solution. We have seen solutions of this type in many places, fuses. As a matter of fact, and while I'm talking about that, I might as well share with you this piece of information, which is very important for our field. The Army Corps of Engineers was charged 200 years ago with working on the flood control of the lower Mississippi, actually the entire Mississippi, all the way from Minnesota to New Orleans. And they were given the control, the hydraulic control of the Mississippi since the beginning of the nation's history. It was in around the early 1800s. And what the first thing they did is they said, well, we're going to control the floods by building dikes. We're going to build a dike on the left side, a dike on the right side. And they started with 3 feet. I remember the story as the story goes. They started with 3 feet, or was it 10 feet? No, I think it was 10 feet. 3 feet is nothing. So 10 feet of dike in the lower Mississippi. That was, I would guess that it was around 1820. It could have actually been 1800s because the nation started in 1776 and the Army Corps was there already, the Army Corps of Engineers. So they were given the job to control the floods on the Mississippi, as if the floods on the Mississippi could be controlled. Let me say that. They were given the, repeat, they were given the jobs of controlling the floods on the Mississippi as if this could be done. And now we know that it can't be done, right? And I'll explain that in more detail later on. But these gentlemen, Army Corps engineers, started doing this work primarily by building up levees on the left side and on the right side, on both sides. This particular piece of civil engineering work has been regarded in terms of volume as the largest ever built in the US and perhaps in the world. I'm not sure how it compares with the Wall of China. I have not done that calculation, but it is a big structure. From its inception in the early 1800s to now, to the late 1900s, like 200 years, it grew from 10 feet to about 35 feet. Go back and check it, find out. Google tells us everything nowadays. It may not be perfect, but it is enough for us. 35, 36 feet. So it's been huge. It grew up. And why did it grow up? Because the Army Corps needed to make, it so happened that their structure was always it was spilled over, so therefore they kept building it up, and now it's at 36 feet. So, as McPhee, in his famous book, The Control of Nature, said in 1979, when the Army Corps would touch heaven, it is anybody's guess in terms of how high they were going to get with these levees on both sides of the Mississippi. The situation was not just floods, it was also sediment, because the Mississippi carries a lot of sediment, bringing all the way the sediment from all the states, including some places in Canada. Okay, so that is what they were doing. Now, they underwent 2 big floods. The 1973 flood. I say 2 big floods in the last 50 years since I have memory or I have studies, because I cannot recall all the series of floods over the last couple of hundred years. But I do recall the 1973 because it was widely documented. The Army Corps almost lost everything in 1973. What does that mean? And we will talk about that later in more detail. And I encourage those of you that are interested in the hydraulics, the sedimentation, or even the history of this problem to go back and pick one of the subjects that I have identified for you as a project for this semester. So in 1973, they almost lost everything because the famous old river control structure, which controlled the old river, almost failed. It was at the brink of failing. And if it didn't fail, it was because, I guess we could say, God didn't want it to fail at that time. Okay, so they're really scared because had the system that they had in place failed, the Corps would have lost control of the Mississippi. And the Mississippi would have gone elsewhere, not to New Orleans, where they wanted it to go. It would have gone into the Atchafalaya, which is a distributary of the Mississippi. That's another story, and we'll get back to that later on. So basically, just by virtue of destiny, the Corps did not lose, let's put it that way. Then 20 years later, in 1993, in the meantime, by the way, the Corps decided to reinforce their structure, and they ended up building the new Oil River Control Structure, which was one more piece of concrete to withstand the force of nature in the delta of the lower Mississippi. And so they did. I was there, as a matter of fact, in 1983 or 84 when the project was being built. I stood on that structure as it was being built. I'm talking about the old river, the New River Control Structure. So at any rate, that's past story. Now in 1993, when the two control structures were already operating, the Corps had another problem. They had the 1993 flood, which apparently, and I can't verify this for a fact, but is strong or stronger than the 1993 one. But of course, now they had the second structure in there. But yet they were so concerned that despite the second structure and everything seemed to be under control, the water levels were endangering the structure, meaning the water levels kept rising, without control, and the flood was not receding. That's when they went big on the issue of fuses, and that's why I'm talking about this right now. They came up with the idea that they had to blow the levees, just like was done in the year 2011 over in the Bird's Point. Okay, they blew 200 levee fuses, and these are not levee fuse like this one that is purposely engineered to breach. No, what they breached over there was the actual dike. As the story goes, it was reported that in 200 sites throughout the lower Mississippi, perhaps even going up higher or further north, further upstream, they had to blow 200, which kind of tells us that they were not in control. If they had to destroy their own work before losing it all, they were typically not in control. So at that point, the Army Corps decided that the hydrology and perhaps hydraulics that they had been using for 100 years were not worth a darn. And they went back to the drawing board. The first thing they did was to retire, or technically junk, the so-called physical model of the lower Mississippi, which was sitting around or outside of their Vicksburg lab, Army Corps Waterways Experiment Station at Vicksburg, Mississippi. They basically decommissioned the model because it wasn't telling them anything. And right now, I believe, I haven't been out there. I was at Vicksburg once, but not to the museum. Right now, it's a museum to show the world or the people that visit some of the work that went on there in the past. So that's the concept of the fuse, okay? Long story, but important from our standpoint.
Professor Simons, you always ask the same question on the prelim. Why? Simons responded with a smile. It's simple. Whoever does not know the answer, I flunk him.
And here's the answer. There's a particle dropping. The question is, what's the velocity distribution between the particle and the edge? This is the velocity. This is the shape of the velocity distribution. The particle, this is the detail. This is the wall of the flask, and that's the velocity distribution, right in the center of gravity of the particle. And it's steady, by the way. It's supposed to be steady because the particle is falling at a constant velocity, or fall velocity, I guess you could say. Why is it like this? For two reasons. First of all, since there's no hole, no vacuum in here, whatever is going up has to be coming down. There's no question about it. So the part that is next to the particle is actually moving with the particle. But the part that is sits or it is far from the particle, between the particle and the wall, has to be going up. That is intuitive now that we have seen it. But it was not intuitive if you had not seen it or were not explained. It was not explained to you. But the issue is, why here? Why does it, first of all, you have to have a balance. So this area has to be the same as this area. And also this has to be zero. Why? Because the flask is not going anywhere. It's not moving. So therefore, the velocity here has to be zero. So this is then the shape of the answer. Oh, that's the answer. That's the answer that Professor Simons asked every one of the graduate students that went through his program in the prelim exam. In a doctoral program, you have two exams. Well, at Colorado, we had two. The prelim exam, which is given within a year, after a year of being there, and then the final exam, which is given when you present your thesis after 3 years, usually 3 years. Some people do it a little faster, and yet others do it a little slower. But I did it in 3 years. I thought that was the norm, and I worked myself in order to get that accomplished in 3 years. So this is the question that was being asked of all the students. And since it was a question that most people really knew, then because everybody talks, you know, oh, this is the question. And therefore, Simons felt that that he could ask this question to make sure that the candidate was on the ball and knew the information that was discussed in the hall. Now, I'm not sure if actually Simons ever flunked anybody that did not know, but that's what he said when he was quoted or he was asked about this. Okay, so now sit tight because we're going to go into something that is extremely unusual. And that is, first of all, I'm going to show you the vector. I always have a vector and a raster. The raster is the movie, and the vector is to show the story. So this is the same question, and I already talked about this, so I'm just going to move forward in here. Notice this picture, which is one of my pictures, famous picture, bank erosion on the Apa River along the border between Brazil and Paraguay. I had the good luck of having a job when I was young, in the year 1979. I had a big job over in Brazil. So I went over there several times and learned a lot. A lot of stories came out of that experience. And I visited the entire upper Paraguay basin from the top to the bottom. I had to go east, west, north, and south, just because I felt that it was necessary so that nobody would argue with me when the time came to discussion. And if somebody says, hey, have you been here or have you been there? I was ready to say, yes, I was already there. Okay, so I decided to go to the end of the watershed, the Apa River, which is the border between Brazil and Paraguay. And I was there for a few hours and took some very nice, good pictures, particularly this one. What is this? Well, this is the Apa River. And why does it look like that? Because the Apa River meanders. And when it meanders, it cuts, and then it breaks. And I think I've shown you, or I will show you eventually, another picture a little bit further upstream or downstream, where all the sediment that had come out of the bluff over there had not been removed and was still sitting there waiting to be removed, because that is the action. Now, meandering, the rivers meander. Should rivers meander? The answer is, of course, they will always meander. Why? You know what? We don't really know. Einstein was very close. I think we don't know the exact details as to why a river meanders, but we have a hunch. And one of the major hunches, which was postulated by Einstein, by the way, in his famous 1926 paper, it's because they have to meander. God says they have to meander. Why? Because the rivers are hanging on the earth. Imagine the earth and a bunch of rivers, and they're hanging there by gravity. Gravity is the first force, right? in space. They're hanging in space, and they got to do something. They move. They actually end up moving. And the motion is such that it produces what in dynamics is called preferential modes of perturbation. In other words, a straight line will become a curve. And it will become a curve, and it would have a certain frequency or wavelength. And then it would continue changing and so on and so forth. Long story made short, this is a very tough subject, and I don't believe anybody has the actual answer to this so-called problem. I already told you at the beginning of the class that a friend of mine in Colombia has a company where he designs and constructs these odd guard veins that are supposed to make sure that the meander does not meander, or that the river does not meander. And I think I already told you that my friend had, by the time we had this discussion, that was 5 years ago, he had built 18 projects and one of them had failed. As a matter of fact, when I was there, the first time I visited his projects back in the year, I believe it was 2001, roughly like that. He had been doing this for 10 years. Now it's 30 years that he has been doing this. So I told, he's a very good friend of mine, and we joke a lot. And I said to Carlos is his name. Carlos, I said, it just occurred to me that you're a time engineer. And he said, what do you mean? I said, I just invented that term right now, but that really fits the work you do. And he said, what do you mean? And I said, well, it's just a matter of time before your projects are going to fail. He laughed, but he understood that I had spoken correctly, because 20 years one project failed. Who is to know, maybe 20 more years another project will fail. And then 20 more years another. Of course, he's not going to be there. He obviously has to go, eventually he has to go to heaven, like me, right? But the point is that in time, these projects will fail. We try to do the best to make sure that they don't, at least in the time we are around. But all these hydrology projects will eventually fail. The question of the defense of the lower Mississippi, the so-called old river control structure and new river control structure, which I already talked to you about, it is a matter of time before they will fail. The Corps is charged with not letting that happen. But the Corps, like anybody else, are humans. They're all human. They can fail. So we could see the time in the future, certainly not in the next few years, where these projects will be endangered and maybe even fail. That is in the cards. And that's why we have to prepare for that, at least to accept that that is the fact. Okay, so that is the story on this. Now, a couple years ago, I signed up a student of mine overseas, virtual student, who is very mathematical. I realized that because I queried him. I asked him whether he knew and so forth. He was going to help me do some work. And I realized that he really knew his math. Now, I liked math, but I'm an old man. I can't do that math anymore. If you want to do this kind of math, you got to be young, okay? Right out of school or within a few years out of school. So his name is Jonathan Mejia. And I posed to him the question. I said, Jonathan, and I said, Jonathan, it's Jonathan. I said, Jonathan, this is the problem. We have not calculated the actual numbers, but this is the problem. That's the way it's supposed to go. So please do the calculations necessary to show the calculation given a certain flask diameter, given a certain particle diameter. Tell me what the distribution is. Meaning, tell me where the point where the positive and the negative velocity distributions are equal, or rather, where they match. They have to match somewhere in the middle. So that he did. He spent, I don't know, a month or so doing this calculation. And then we had to clean it. And then I had to go in there and check it all because, you know, Professor Ponce is an expert on HTML. And not many few people are, by the way. That's a story that could be told. For some reason, well, I know the reason. I can share with you the reason, but I'm not going to do it because I basically end up creating enemies. But the point is that very few people can master the HTML the way I had done it in the last 25 years. So I had to go in and fix everything, or rather correct, or rather check everything that he had done. So at this point, I'm going to show you the work that he did. The subject is spatial distribution of steady flow around a vertical particle falling by gravity inside a water-filled flask. Classical sedimentation project. And I know Professor Simons would have never attempted to ask that anybody solve this problem as Jonna did, because too difficult. It would have taken a complete project for somebody to do this. And in fact, Jonna did it, spent some time. He knew his math and he spent some time on it. So we have in here this paper. It says, this article aims to answer the question asked by Professor Daryl Simons at Colorado State University in the mid-70s. The problem is to determine the spatial distribution of steady flow around a spherical particle falling by gravity inside a water-filled flask. Given the diameters of the particle and the flask, we invoke the fundamental law of the conservation of mass and use volume integrals and the mean value theorem in order to come up with the answer. So the first thing we need to do in here is the fall velocity. And the fall velocity, well, we have a formula for that. And you're already familiar with that formula. As a matter of fact, I do believe I said that earlier, you're going to be working with this formula. Or the next formula, I think it is what it is. But one of these two formulas that I put in the book, I want you to derive, because we had to sit down and derive them too, by the way. So I want you to kind of recreate the work that we did where we wrote the book more than 30 years ago. The velocity distribution in the space within the particle in the inner wall has the following characteristics. The center of the particle is at the origin, right here. And by the way, this is in Spanish, namely because Jonna is Peruvian. He's from the same country where I originated. He's actually in one of the towns of Peru. He's a graduate of hydraulic engineering in the main university there. He's about 5 years out of school. So this is in Spanish. What I should do is I should redo this in English, which can be done readily, by the way. I'm going to ask him to do that, because I was not completely aware that this was, because what we had done is we had done a version in English and in Spanish, but we forgot to do the graph. But it doesn't matter. You can see this is not that difficult to understand what's being said in Spanish anyway. Distribution of velocities, the interior wall of the flask, and the fluid, and so on and so forth. So what do we have in here? We have the center of the particle is at the origin. The flow close to the particle is given by Q1, this Q1 in here, while the flow close to the interior is Q2. These flows, the flows have to be equal, not the areas, mind you. It's not an area, it's the flow. The flows are equal due to the law of conservation of mass. The value of V1 is the fall velocity of the particle, right over here, V1. The value of V2 is the maximum upward flow velocity, V2 over here. The boundary condition of the inner wall of the flask is the no-slip condition, V sub O V0 equals 0. The value of C is over here, is the point of intersection between the velocity distribution with the y-axis, or rather with the x-axis, and it is where the equilibrium of the two flows, Q1 and Q2, is established. So the process calls for the calculation of Q1 is already known, Q2, and also the location of C. If that can be done, then we'll solve the problem. Because this is a parabola. This is technically a parabola. So now sit tight, because what you're going to watch in here probably you had not seen before. I'm just guessing. Maybe you have. You have. You tell me. Okay. So we have in here the mathematics required in order to solve this calculation. And I show you this, first of all, because we're very proud that we did this. I certainly did not intended to, but I took the opportunity. And second, because it is a tremendous amount of work to do this. And what sedimentation is work. And I wanted to show you how this is done in practice. So we're evaluating the equations in here. We state the conservation of mass, right? You have to follow the conservation of mass. Mass is the basic law in here. So the conservation of mass over here in the volume integrals, and here is the generation of the surface of revolution below the origin of ordinates. And continuing with the volume integrals, or shear, and this is the actual surface being generated with CAT, MatCat, I think, or MATLAB. I'm sorry, not MatCat, MATLAB. So that's the parabola upstream and the parabola downstream. We continue with the calculation. We finally have an example where we calculate the C. In this case is 0.01. For the case of diameter 1 millimeter and the total diameter 6.5 is the flask diameter. This is just an example, and we're going to be using the calculations, particularly equation 42, in order to get the answer. And the answer is 0.16. So if you consider that 6.5, so that means that's 3 centimeters over here. From here to here is 3 centimeters. And now the answer is, for this particular problem, is 1.6 centimeters. It's the C. In other words, the distance from here to here, 1.6 centimeters. Okay, so that's correct, and that's the end of this problem. That's the end of this problem. Conclusions. The spatial distribution of the steady flow around a spherical particle falling in a flask filled with water, quiescent water, has been calculated. Given the diameters of the particle in the flask and using the fundamental laws of conservation of mass and volume integrals, the coordinates of the point P2 are calculated, which separates the upward flow close to the inner wall of the flask and the downward flow adjacent to the particle. Okay, from here now then we move on to the initiation of motion using the Shield Criterion online program. There's also the issue of initiation of motion based on fruit number, which we hope to get afterwards. We're not going to have time probably today, and we're making good progress, so we're not in any hurry here. But let me just say that first we're going to use the Shield Criterion, and this is an online program. This is an online program, and this, I believe, we already explained to you. I believe we explained to you. Particle diameter was at 3 millimeters. The flow depth 7, the channel bottom 0.0001, I believe, and water temperature 70. I believe these are the numbers. Yeah, that's right. That's exactly the same example that I had already worked or posed to you earlier today. This, by the way, is a kind of a nice sand bed channel. I was talking to you about sand bed channels. Those are the beds of the channels that we care to look into because they are the majority in the field. Most rivers in the valleys are a sand bed. Interestingly, though, and I should talk about this because eventually we'll talk about morphology and sediment transport and so forth, but if the bottom of the river is sand, it already kind of depicts a certain slope, and the slope is on the order of 0.001. 0.001. Because if it's 0.0001 or even less than that, it will have a little silt. And if the slope is steeper, like 0.01 or even greater than that, it will have some rocks or some ripples, not ripples, but cobbles. So it goes without saying then that when you look at a river, if you're experienced, you can almost tell what's the slope, within a certain range, the slope of the channel. In this case, of course, we're talking about a slope that is 0.001, which is 0.1%, roughly. This particular channel is in the Tijuana estuary. The Tijuana estuary has a bunch of channels out there. I'm not quite sure. I believe this is a distributary, not a tributary, but a distributary. This is interesting because it is in the estuary. The estuary of the Tijuana River, as you know, is here right in town, south in Imperial Beach. So this picture was taken, I believe, back in the year, it had to be the early 2000s, maybe 2002, 2003, at Imperial Beach to kind of show what we are doing in here. I should mention to you at this point, those of you that have been puzzled by the quantity of information in my site, that we've been doing this for almost 25 years, and we currently have about 1,200 or 1,300 rotary pictures that I talk about. I talk about the rotary pictures, like in here, right there. If you click on refresh, you get another picture. If you click on refresh, you get another picture. And all these, every one of these pictures has a story, and it's part of a project that we have been. So usually I would go to a project and I would take maybe 10, 20 pictures, actually take more like 300 pictures, and then choose 10 and expose or show only 10 because they are the best ones. Like in this case, we had this watershed over here that that had very steep slopes on the sides, almost 40 to 45%. We had not seen that in any other place. This is very unusual. And this is in the Andes, in the Moyan River, in Lambayeque, northern Peru. And continue, like I said over here, this one is a channel that was put together by the Caxa culture back about 3,500 years ago. And the channel is still there. As exemplified, I was there in the year 2014 and took the picture dated, the channel is dated 1,500 years before Christ. So each one of these pictures, and you're welcome to browse through if you have time, like maybe during the week or something. This one is not a picture that I took, but it was such a fascinating picture that I felt compelled to show it to our viewers. The Colorado River is a fascinating river, and it is the livelihood or lifeblood of many states, seven Western United States, including California. I believe the percentage, I'm not sure, but I believe, no, I am sure. I believe a fifth of the 16 million acre feet, 4 go to California. So we get 25%. Our allotment is 25%. Of out of the 7 states, we get the lion's share because we have more people and political power and so forth. But if you go above the Colorado River, beyond Arizona, beyond California, then beyond Arizona, then get into Utah, you get into very unusual situations. And this is one of them. This is the confluence of the Green and Grand Rivers near Moab, Utah. This is a tributary of the Colorado River. As you can see, a lot of sediment out there in constant motion. Why is the Colorado River referred to as Colorado? That's interesting. The name Colorado is a Spanish name, which means reddish or brownish. Let's say brownish reddish. So why this Colorado River was there prior to 1845, which is when the government of the federal government in the U.S. took possession of California. So they didn't bother to change the name of the river. It was the Colorado River. The Colorado River was given that name by the early Spanish explorers of the 16th and 17th century. I believe the date was around 1600 when they showed up for the first time on the shores of the Colorado River. And what they did, they named it eventually. Of course, they were there to discover and to name. They named this river the Colorado because it was reddish. It was brownish reddish. And it has remained, the name has remained. Interestingly, and with here, I'm going to finish in here. Interestingly, the Colorado River, named by the Spanish explorers more than 300-400 years ago, if you look at it upstream of the 2 big dams that were put together by the Bureau of Reclamation in the 30s and 40s, it's no longer Colorado. Meaning, downstream of the two dams is not Colorado. It's already a river that looks more greenish and bluish. Why? Because the sand is being retained by the two dams that are out there. These two dams, Glen Canyon and the other dam, I don't remember right now. You know this. One of them is right next to Las Vegas, within driving distance from Las Vegas. Um, they retain the sediment. The sediment is being retained behind the dam. That is one of the major issues of hydraulics at this point, an issue which has no solution. And I will endeavor to talk about this extensively as we move ahead with the class, because this is a problem that remains to be solved. In other words, we build a dam because we want to hold on to the water, but we end up holding on to the sediment too. That we have not been able to flush the sediment or to do something about it. And that's where we stand right now. So the criticism to dam construction, one of the criticisms is that eventually it's going to fill up with sediment. I think I already mentioned to you situations where this happens all over the world, not just here. Okay, but we continue to build the dams. I think we have about 1,000 dams in California alone, because we need to shower every day. We need the water every day. The towns, the cities require the water, demand that we have the water, and we can use the water properly or improperly or whatever, or wasted or not wasted, but eventually we're going to have to come up to cope with the realization that the water is going to run out for the needs that we have, because the population continues to increase and the demands continue to grow while the amount of water appears to be kind of not quite. And I don't want to throw in a monkey wrench of the global warming, because we'll never get out of their argument. At this point, people don't really know what's going on in terms of the global warming at this point. So that's a good story on the Colorado. And I'm going to finish in here. I have 1 minute on the meandering. The meandering is an unsolved problem also. Our friend in Colombia is trying to solve it. No, he's not trying to solve it. He's trying to fix it temporarily for the bosses that want the quick fix. But he's not solving the problem, because I already told you, he's a time engineer. Eventually, his structures will fail. So that's the example of a river that I worked on when I was in Brazil back in the year 1979, 1980. This is the Miranda, Aquirahuana River and the Miranda River, meandering in the middle of the vast forest out there in central western Brazil. So with that, I am going to finish in here. If there are no questions, I can entertain maybe a minute or two of questions. If not, we'll continue this Thursday. Thank you very much.